All right, let's take a look at our second example problem. So steam at 5 bar, 300 degrees C is condensed to saturated liquid at 5 bar in a heat exchanger at a mass flow rate of 1 kilogram per second. Cooling is provided by water, which enters the heat exchanger at 20 degrees C in 1 bar and exits at 60 degrees C, neglecting pressure drop in pipes and heat losses to the surroundings. Determine the flow rate of the cooling water, the amount of heat that it's exchanged, and the rate of entropy generation. All right, this sounds like a great one. So we're going to perform an analysis of a heat exchanger. Okay, and so flowing in, which I'll label as stream 1, I'll have steam, which is at a temperature T1 of 300 degrees C and a pressure of 5 bars. Okay, so the state of my system specified. I have temperature and pressure. Okay, then that's going to be cooled. Okay, so I'm going to draw a dotted line, continuing this out of my heat exchanger. So my water, so steam, is going to exit as a saturated liquid. So it's going to be a saturated liquid at, so this should be at a pressure of 5 bars as well. So P2 is equal to 5 bars. Okay, so I'm going to have steam at 5 bars, 300 degrees C, that's being condensed, right? Heat's being removed, so it's condensed and leaving as a saturated liquid at 5 bar. Mass flow rate, okay, m dot. Okay, so we could call this m1, but I'm going to assume steady state, m1 dots equal to m dot 2, which is going to be equal to, I'll just call it, we'll just leave it as m dot 1 is equal to m dot 2, and that's going to be 1 kilogram per second. Okay, and then it's going to be cooled using water. Okay, so my cooling water in, I'll call this stream 3. So cooling is provided by water, which enters at, I'll call this T3 is 20 degrees C. And my pressure, P3, is equal to 1 bar. All right, now I know at 1 bar my saturation temperature is 100 degrees C, so this is going to correspond to compressed liquid. Okay, then coming out, okay, or exiting, I'm going to have my cooling water now is heated up to a temperature of, so I'll call this stream 4. My cooling water is now warmer at 60 degrees C. I'll assume that the pressure is still 1 bar since we're not told otherwise. All right, and we're just dealing with our cooling water here, which is going to absorb heat and it's going to increase in temperature. And at 1 bar, I know that my saturation temperature is 100 degrees C, so this is still going to be a compressed liquid. All right, so now we have everything labeled, and what we're asked to solve for, so we're asked to determine the flow rate of cooling water. So my cooling water is going to have some flow rate. So again, we'll assume steady state. So m dot 4 is equal to m dot 3, but that's unknown. So I'm going to solve for the mass flow rate of cooling water and the amount of heat that is exchanged. All right, so I'm going to assume that any heat leaving this stream here with my steam, right, for process 1 to 2, any heat that's removed from that stream is absorbed by my cooling water. Okay, so let's calculate the flow rate of the cooling water and the amount of heat that's exchanged, and then after we do that, let's think about entropy generation and what we have going on there. Okay, all right. So first, okay, I'll call this just A, where A is I'm going to solve for Q, and then I'm also going to solve for, I'll just label it as m dot 4, the mass flow rate of my cooling water. All right, so I'll start with a first law balance on stream 1, 2, right, of my steam. Okay, so I'll start with my first law balance for my open system. Okay, so du total dt plus delta. I have change in kinetic energy. Okay, plus change in kinetic energy plus change in enthalpy. Remember, enthalpy, not U, because my fluid element needs to displace the fluid element in front of it. Okay, du total dt, this is U total, my extensive internal energy, units of energy per time. M, as I have it written here, would be my specific mass, or specific enthalpy, energy per mass. Here is mass per time. Right, the units would work out. And that's going to be equal to, whereas Q dot plus W dot. Okay. All right, so next, let's make some simplifications. Okay, so simplification 1 is I'll assume steady state. Okay, so I'm going to take du total dt to be equal to 0, and then also m dot 1 is equal to m dot 2. Mass flow rate in is equal to the mass flow rate out. Otherwise, we'd have an accumulation of mass in my system. So we'll assume steady state. Okay, assumption 2 that I'm going to make is I'm going to assume that the change in kinetic energy and potential energy is negligible. Okay, cool. And so this term and that term will be 0. Okay, then 3. Okay. In the problem, all right, we're not given anything that suggests that there's any sort of work produced or work done on our system. Okay, essentially there's no shaft work present. Okay, so I'll take W dot to be equal to 0, right, that there's no work exchange. So when we do all that, okay, what I'm going to end up with is that I'm going to end up with then H2 minus H1, right, so delta H. Okay, m dot, we had, m dot 1 is equal to m dot 2. Let me just call it m dot 2. Okay, m dot 2 and m dot 1 are the same. So let's just call this m dot 2 is equal to q dot. Okay, and when I have q dot here, I'm going to write this as q. Let's write a q12, right? Just so I'm referring to that stream up top there. Okay. Cool. So if I wanted to solve for the heat exchange, q dot, I could solve for it, as such. And what I'll need to do is I'll work out my equations first, and then, well, actually, let's get everything first. Okay. So H2 and H1. So I can get those from my steam tables. My inlet and exiting stream so stream 1 and stream 2 are fully specified. We're given the mass flow rate, so we can solve for Q dot. Okay, so actually I'm not sure if I have my steam tables open. So let me get my steam tables open. Okay, so my apologies. Okay, so let's scroll down. Actually, let me pop this up here. So I'm going to go to my steam tables. Okay, and what are we looking for? So we have a stream at 300 degrees C and 5 bar. So let me go to my superheated steam tables. Boom, boom. So at 5 bar, my saturation temperature is 154.84. Okay, so I'm going to have a superheated vapor. So I'll read across to 300 degrees C here. Okay, and then I will need the enthalpy. What I will record is I'll record the enthalpy and also record the entropy, because I suspect I'll need it for my entropy generation calculation. Okay, so I will get H1 is equal to So H1 is equal to, so 300 degrees C, 5 bar, 3064.6. And that's kilojoules per kilogram. Okay. S1 is equal to 7.4614. Okay. Let's get H2 and S2 while we're at it. So now we're going to have a saturated liquid at 5 bar. Okay, so I'm going to have a saturated liquid. So let me get enthalpy and entropy of my saturated liquid. So it'll be this one. So H2 is 640.19. 640.19. S2 is 1.8606. And let me also just record the T2, okay, is going to be 154.84. Okay, so we're actually cooling down then from 300 degrees C to 151.84 degrees C, and we're also converting from a vapor to a liquid. Okay. All right, so I just want to confirm my units before we move on to the next part. Okay, so S is kilojoules per kilogram Kelvin, H is kilojoules per kilogram. All right, so H we got right, so kilojoules per kilogram. Okay, and then this is going to be kilojoules per kilogram Kelvin. Bam. All right, so we have that. We have m dot, which is 1 kilogram per second. So we can go ahead and we could solve for q dot, and yeah, that'll be in kilojoules per second. Okay. So I'll jump over to MATLAB in let's just do it now. So let's go to problem 2. Okay, and so let's record what we have. We have H1 is 3064.6. H2 is equal to 640.19. And we just need, we'll call it M2, which is 1. All right. Okay, so Q dot, so I'm going to call it Q12. Okay, so this is going to be an energy in kilojoules per second, is going to be equal to M2, which is in kilograms per second, times H2 minus H1, which are in units of kilojoules per kilogram. So I'll get kilojoules per second. Okay, so running, I get big Q, so that's times 10 to the 3, so negative 2,000. Okay, so I'm going to get Q dot 12 is equal to negative 2,424.4, and that's going to be kilojoules per second. Okay. Cool. I think a kilojoule per second should be a kilowatt, right? But we'll just leave it as kilojoules per second. All right. So now we need to solve for the mass flow rate of my cooling fluid. And so I'm assuming, right, so we get that Q is negative. So that means heat's removed from this stream 1, 2. So we're going to assume that the heat that's removed from stream 1-2 is absorbed by stream 3-4. Okay, so if I were to perform my first law of balance on stream 3-4, so let me just say 3-4, okay, all right, we would make the same exact simplifications and we would get exactly to the same form of the first law. Okay, so we would have that H4, and the way I set up the problem, right, higher numbers might exit. So we would have H4 minus H3, and then we could use m dot 3 or m dot 4, they're the same, is equal to Q 3-4. Okay. So again, we're assuming that any heat that's removed from stream 1-2 is absorbed by stream 3-4. So Q 3-4 should have the opposite sign or be equal and opposite of Q 1-2. Okay. So therefore, we would get that m dot 4 is equal to negative Q dot 1-2 divided by H4 minus H3. All right, so now I need to get H4 and H3. So the assumption I'm going to make is I know I have a compressed liquid. So let me just, where am I going? So I'm going to assume I have a compressed liquid. Why? Because I know that at 1 bar my saturation temperature is 100 degrees C. Okay, so I have a compressed liquid. So what I'm going to assume, okay, and so essentially the assumption that I'm going to make is that the enthalpy of my liquid at saturation, okay, and this is just, I'm trying to write a general equation here, which would be at some T in corresponding saturation pressure Psat, is going to be approximately equal to the enthalpy of some compressed liquid at the same T, but at some P, where P is greater than Psat. Okay, so what I'm going to assume is that at 20 degrees C and 60 degrees C, that I can just look up the enthalpy and entropy for my steam tables from the corresponding saturated liquid at those conditions. Okay, so I'm going to go to my steam tables, and this time I'll go to my saturated steam table since it's sorted by temperature, and 20 degrees C would correspond to stream 3. Okay, so remember at 1 bar, saturation pressure is 0.02, sort of pressure greater than saturation. And I'm going to read off the enthalpy of my liquid. So this would be H3. Okay, so H3. Okay, let me box this in since that's our working equation. H3 is 83.92. Hey, notice even for my liquid, right, my internal energy and enthalpy is essentially the same, right? That PV term is negligible. Okay, so HL 83.92, 83.92. Let me get S3. S3 would be 0.2965. Okay, then let's get state 4, H4 and S4. So in state 4, I'm at 60 degrees C. So let's go down to 60 degrees C. So Psat's 0.1995, right? So P is greater than Psat. I'm a compressed liquid. So let's get HL, which is 251.15. And S is 0.8312. Okay, this is kilojoules per kilogram. Kilojoules per kilogram Kelvin. And we are good to go. All right, so let's hop over to MATLAB, and so I solve for that mass flow rate of cooling water necessary. So let's type in our enthalpies. Actually, let me just keep listing them right up here. So H3 is 83.92. H4 is 251.15. So my mass flow rate, which should be in kilograms per second, I'll call it M4, is equal to negative Q12 divided by H4 minus H3. All right, negative Q makes it positive. H4 minus H3 is positive. So good. So mass will be positive. So my mass flow rate is 14.4975. So the required mass flow rate of my cooling water is 14.4975. And that's kilograms per second. All right, so I've got my heat. I have my mass flow rate. And again, joules per second should have units of watt, so you should be able to change that to kilowatt. But all's good. So we have the flow rate of cooling water, the amount of heat that's exchanged, and then last we're asked for entropy generation. All right, so entropy generation. Let's take a crack at this one. So the key is, I like to think in terms of my entropy generation equation from chapter 4, right? And I use that in the first problem. Right? Let me write it down there, and let me adjust it now since we're dealing with rates, right, of what that looks like. So in general, when I think about entropy generation, it's going to be Sgen is equal to delta S of my system plus delta S of my surrounding. Okay. So now I'm going to need to be careful here in what I'm calling all of these things. Okay. So it tells us that we're neglecting pressure drop in pipes, that heat losses to the surroundings. So we're neglecting heat losses to the surroundings. Okay. So when I perform this entropy balance, right, I'm going to take, right, my heat exchanger to be my system. And I don't think it wasn't necessarily clear, but in part A, right, when I did my first law balance on stream 1-2, right, essentially stream 1-2 was my system, if you will. When I did my balance on stream 3-4, right, stream 3-4 was my system. Okay, that's great. As I think about entropy generation now, right, I'm going to take, my entire heat exchanger, which is composed of, I have stream 1 and 2 coming and going, stream 3 and 4 coming and going. Because what we're told is that we're assuming no heat loss to our surroundings, right? Because any heat that's lost by stream 1-2 is absorbed by stream 3-4, right? So, the net, effect is that, Q net would be 0 for this system, right? That there's no heat loss to the surroundings. Okay, so when I write down my entropy balance, okay, right, we're told that delta S of my surroundings is, so when I think about delta S of my surroundings, right, what I'm thinking of is this is equal to Q bath over T bath, okay, but we're told, right, that no heat, right, it leaves our system, right, so delta S of surroundings is going to be equal to 0. So we're going to be left with Sgen is equal to delta S of my system. Okay. Now what I need to do is I need to write this in the context of my open system problem here. Okay. All right, and so what I need to do, okay, is in general, okay, or how I'm going to have to write this is Sgen, okay, for my open flow problem, Okay, I'm going to write this as S dot gen. So now Sgen is my extensive entropy generation per unit time. So Sgen is my extensive entropy generation per unit time is going to be equal to, okay, now in terms of delta S of my system, okay, how I'm going to have to expand that out is I'm going to have entropy flowing in stream 1 and flowing out in stream 2. Okay, and so that's going to be equal to, I'm going to write it as m dot 2, since m dot 1 is equal to m dot 2, my mass flow rate of stream 1, 2 times specific entropy of my exit minus the specific entropy of my inlet. Okay, plus, okay, now I need to do the same thing for stream 3, 4. Okay, so that'll be equal to, or plus, m dot 4 times exiting S4 minus S3. Okay, so I started with my Sgen equation from chapter 4. Okay, key here is that we're told, and so my system is my heat exchanger, which is made up of stream 1, 2, and 3, 4. We're told that there's no heat exchange between my system and surrounding. So delta S of my surrounding, right, is going to be 0, since the heat, released to our surroundings is 0. So Q bath is 0, so delta S of surroundings is 0. So we're left with just Sgen is equal to delta S of system. Now I just need to extend this for an open system. So this is S dot gen, and so this would be my extensive entropy generation per unit time, and then we're counting for my streams flowing in, right, in terms of S1 and S3, and out is S2 and S4. All right, and we have all of that information tabulated. Okay, and our units are going to be, our mass flow rates are in kilograms per second, entropies are in kilojoules per kilogram second. So this will be kilojoules per Kelvin second. Yeah, kilojoules per Kelvin per second. All right, so to get Sgen, well, I'm going to need to add S1, S2, S3, and S4 to my sheet, where these are kilojoules per kilogram Kelvin. So S1 7.4614, S2 1.8606, S3 0.2965, S4 0.8312. Okay. So then Sgen, okay, and keeping track of units, okay, this is kilojoules per kilogram second. We're multiplying by my mass flow rate, which is kilograms per second. So Sgen will have units of kilojoules per second Kelvin. So kilojoules per Kelvin second. So Sgen is equal to, so I called this M2 up here, M2 times S2 minus S1 plus M4 times S4 minus S3. And we get Sgen, it's positive, perfect, right? We expect it to be an irreversible process. All right, so we expect this to be irreversible. So you get the Sgen is 2.15 Okay, again, this is a rate, so this is going to be kilojoules per Kelvin second. Okay, cool, and that's it. Okay, um, in terms of converting from our rate, all right, so if we go up here, so if we go to so power, right, 1 watt is 1 joule second, right? So if I wanted to, okay, I could rewrite sgen, right? I could say that s dot gen is equal to, so a kilojoule per second would be a kilowatt per Kelvin. So I could write this as 2.1510 kilowatt per Kelvin. Okay, and then Q up here, right, this would be kilowatt. So I could equivalently say this is equal to negative 2,424.4, and I could write that as kilowatt. Yeah, because a kilojoule per second is just a kilowatt. All right, so there is our analysis of a heat exchanger. So yeah, that was fun. If you have any questions, let me know.